So we're actually going to have one of our Ds give a talk about some of the work that he's been doing that was initiated by this award and has gone on to get his own funding. Dr. Tim Lucas. All right.
Well, thank you very much for that introduction. I was hoping for a minute you were going to give my talk for me, which would have made it much nicer for me. I have no financial disclosures germane to this talk. Before we get into the science that was enabled by the K12, I wanted to bring your attention to two unsung champions of neurosurgery research. So don't go far, Ahmad. On your left, you'll see Steve Korn. As mentioned, he's the Director of Career Development at NINDS. For years, Steve has observed a growing threat on the horizon for neurosurgery research. Fewer and fewer neurosurgeons were successfully competing for NIH funding, and consequently, fewer and fewer neurosurgeons were staying engaged in primary research. But Steve, like everyone in this audience, believed that neurosurgeons can perform high-quality research, we can produce excellent scientific literature, and most importantly, neurosurgeons must be represented in NIH funding priorities. So he put together the K12 mechanism. Ahmad Eskandar put together a brilliant proposal that he called the Neurosurgery Research Career Development Program. This program allows applicants to come from around the country and interview with the advisory panel, meet face-to-face with inspiring, funded neurosurgeons on a one-on-one environment. I think this is the crown jewel of the opportunity that Ahmad has put together. These advisory panel members are really what Tom Wolfe would have described in the 1950s as individuals having all the right stuff, people we aspire to be. So on behalf of the K12 awardees and the applicants, as well as the members of the CNS, please join me in thanking Ahmad and Steve Korn. On to the science, our background. During the Renaissance, it was popular to believe that a touch from the hand of God created Adam. Since then, and half a millennium later, we know that the dexterous hand movements are a defining feature of human existence. Our interactions with the physical world hinge, in fact, on our ability to explore and manipulate objects. In fact, just like the fresco, social interaction is galvanized by touch. Unfortunately, in the modern era, a host of maladies rob us of that humanizing characteristic. Victims of these maladies are the motivation for our work. The state of the field in motor BCI is shown here. Past decades have witnessed tremendous advances in our ability to mobilize, move a paralyzed limb. The best example is this recent demonstration by Beryl, enabled also by Ali Rezai. In this example, non-invasive functional electrical stimulation through the skin to paralyzed muscles allows wrist contraction. This is driven by a Utah ray implanted in motor cortex. This is a wonderful proof of principle for motor or efferent BCI. But of course, movement is only half of the equation. Somatosensory feedback is critical to guide real-time movements. You can regard these four objects here and know that you would manipulate, handle each of these objects entirely differently based on your anticipated somatosensory feedback. Real-time somatosensory feedback is critical for precise movements. If you want to ask how important is somatosensory feedback really, ask a patient who's recently lost it. This is an individual who had primary somatosensory cortex seizures that then secondarily generalized, many per week. Despite numerous counseling sessions that removing of the seizure focus and his lesion would disable his hand, he insisted on moving forward, and so we did. We removed his primary somatosensory lesion as well as the lesion behind it, cured his seizures, and we had an opportunity to map quantitatively what happens when you primarily deafferent the hand. So in this experiment we called the coffee cup experiment, we have the individual hold a load sensor. They would squeeze the load sensor and see a resource meter on a computer screen go up and down. We would give them a target to achieve, and they would hold that target after the visual feedback was removed. So this is very much akin to when you're holding a coffee cup during a conversation. You look away from the coffee cup and yet you don't drop it because you maintain that grip force modulation. Well, he does it perfectly with his intact hand, just like all of you would do without any practice. But on the middle panel, you'll see with the affected hand, once the visual feedback is removed, all bets are off. He either drops it or tries to crush it because he has no somatosensory feedback. The state of the field for sensory or afferent BCI is really shown best here by Dustin Tyler's work. This is an individual, 24 years old, who was a quadriplegic after a diving injury. Scratch that, that's coming up. An individual who has a robotic arm after an amputation, and there is a sensor-enabled robotic arm that he's using to pluck cherry stems. Now the trick is he's blindfolded, so he has to use sensory feedback driven by the robotic arm plugged into peripheral nerve stumps in the amputation. He's able to achieve this task brilliantly. But what about the much more common scenario of someone who has a complete normal distal anatomy, but just no communication between the brain and the body? Well, this is our solution for that scenario. We call it the body area network. It consists of a suite of sensors, implanted, some worn, and brainstem recording devices and stimulators. These are the components of the system here shown. We have the brainstem and brain cortex stimulation and recording device that's implanted in the skull, very much like the NeuroPace system is currently for those of you who are implanting that. Then we have sensors that are implanted underneath the fingertip to allow force perception as well as vibration and flutter. Across joints, we restore proprioception with strain gauges and flex sensors. And across large joints, we need another solution. Here we use electrogoniometers. All of these communicate wirelessly with a watch that you would wear like your Apple or Garmin watch, and that transmits digital data back up to the brain implant. This is our first generation of that system, the prototype that we call the PEN brain-machine brain interface system. All of these systems communicate at gigahertz frequency wirelessly. You'll see in panel A, that's the neural signal analyzer. It can record brain activity as well as stimulate. Below that is the stimulation engine. There's a very large dynamic range for the stimulation engine. We can dial it to microamp output for individual unit activation if you're stimulating in a sensitive area, or we can dial it to milliamp range or tens of milliamps if you want to activate muscle fascicles peripherally. And in this example, we had an active flex sensor, although we've matured on that process. We have numerous generations that have evolved. Each time we have an increase in the channel count, the information exchange between the systems, the battery life expectancy. Now we have memory built into the system, and of course these are all linked by Bluetooth now. We had to develop our own neural stimulator. As you know, all commercial neurostimulators, they claim to be charge balanced, but in fact there's a residual charge right at the tail of their stimulation of the biphasic frequency, and that little charge, a fraction of a percent, builds up over millions of duty cycles to produce electrolytic damage of the electrode interface, and that causes subsequent gliosis. Our system senses the actual zero-point crossing of the voltage with adaptive driving and feed-forward error learning. Now, of course, you can't just start implanting these in patients. You have to work your way up through the phylogenetic tree, and so we begin with rodents. But rodents don't have fingers. So instead, we capitalize on their exquisitely sensitive Beryl sensory cortex, plug our electrodes there, and rats, as you know, are very good swimmers and know Morse water mazes very well. So we employ a task where the rat has to swim in a Morse water maze using a sixth sense given to it by the PEN brain-machine brain interface. Here's the task. A naive rat plopped into the water with the system turned off will swim a random spiral pattern, searching all four quadrants to find that submerged platform. The submerged platform here is shown by a little green cursor that's overlain on the video. The rat cannot see that. Then you turn the brain chip on, and just like a torpedo uses sonar to find its submerged target, the rat searches, detects the brain stimulation, which gives it an orientation, and then homes in, zeroes in right on that target. So we know this system can work in closed-loop operational mode, in fact, underwater, in a physiological system. So then we move to non-human primates. We begin with sedated experiments, mapping the receptive fields to make sure that our system works with high fidelity and is safe. And then we progress into 24-hour, unrestrained, freely roaming monkeys performing tasks using this fully integrated wireless system for closed-loop operation. I'm just about out of time, but I'll conclude with two final comments. The first is that you, neurosurgeons, will play a pivotal role in helping these paralyzed patients by implanting technologies that many groups are developing all in parallel. We will see that on our horizon. This helps patients and it helps us. It grows our footprint in the patient world, and I think it's the right thing for us to consider. And the second is the impact of the K12. This is a bridge fund mechanism that was really conceived by Ahmad and Steve. How do you measure success of this seed money? There's many ways. You can ask any of the 10 of us who have been funded. For us personally, we measure success here. So the K12 enabled 15 papers, 2 international awards at electrical engineering conferences, a National Science Foundation grant, DoD funding, 2 R1 submissions, another NSF funding proposal going in a month, and most importantly, it allowed us to mentor 19 students, 5 women and 5 underrepresented minorities. This is our group. Thank you very much for the time.